Alright, so now I want to explain matching nets, which is one of the most important algorithm for few-shot learning. In fact, I want to explain in this new playlist for few-shot learning, I want to explain these four algorithms. So in lecture 1, I concentrate on matching net. In lecture 2, on protonet. And lecture 3, on relation net. And finally, in lecture 4, on MAML. So today, I will be focusing on just the matching networks. So what is few-shot learning? Given abundant training examples for the base classes, few-shot learning algorithms aim to learn to recognizing novel classes with a limited amount of labeled examples. So at test time, we have n-way k-shot task. When we say k-shot, it means we have k examples. And when we say n-way, it means we have n classes. For example, 2 class, dog and cat. And there are many paradigms for few-shot learning. Many of them draw inspiration from metric learning, some of them meta-learning, such as MAML algorithm that I will explain in lecture 4. And some of them are data augmentation, that we synthesize more data from the novel classes. So this is the architecture. This is the algorithm that I will explain in this playlist. So this is the first lecture, matching networks. So we have a meta training stage in all of these algorithms, and we have meta testing stage in all of these algorithms. In fact, I want to focus on the first approach for matching networks, the first article that this algorithm, this matching networks is proposed. And the rest of these articles, like this one and this one, are very similar to this idea of matching networks. So what is few-shot learning? Learning from few examples remains a key challenge in machine learning. The problem of deep learning is that it is data hungry. It needs lots of data. And so one way to get around this problem is few-shot learning, and even zero-shot learning, which I will explain in different playlists. But there are also other paradigms, such as reinforcement learning, unsupervised approaches like variational autoencoder, and there are many approaches to get around the problem of, for example, labeled data. That labels are expensive, that's why we go and use zero-shot learning or unsupervised learning. As I said, variational autoencoder is a good example of unsupervised learning. But zero-shot learning is very often used when we don't have scene labeled data, that I will explain in a different playlist. But in this playlist, I focus on few-shot learning only. And so we learn from a few examples. And despite recent advances in important domains such as vision and language, the standard supervised deep learning paradigm does not offer a satisfactory solution for learning new concepts rapidly from little data. So few-shot learning is great because just a few shots, just few examples are enough, and we don't need lots of data as is required for deep learning, because deep learning is data hungry. It has many problems. It has curse of dimensionality. And it is very funny because we are using the techniques of deep learning for few-shot learning. As you will see, all of these models are based on deep learning neural networks. And neural networks are data hungry in general, especially if the number of inputs are too high, are too much. So in this work, we employ ideas from metric learning based on deep learning, deep neural features, and from recent advances that augment neural networks with external memories. This is another interesting idea. So the world needs more realistic and complex data. For example, OmniGlot and ImageNet, you see we have very high accuracy when we apply few-shot learning. So the problem is solved for these simple datasets. But mini ImageNet or also biological datasets, there are many datasets that we have very low accuracy, such as 40%, 50%. It's a shame we are in 2023 and state-of-the-art algorithm for mini ImageNet and dataset in biological dataset, such as, for example, biomedical text. We have very low accuracy, but we are in 2023, so it's a shame. So so we should find the datasets that our accuracies are still much below 90%. And so this is the matching net. You see, everything is very simple. We have two neural networks. One of them is f of theta, and the other one is g of theta. So first, and matching networks is a one-shot learning, as opposed to other algorithms that they focus on more than one-shot or few-shot learning. For example, three-shot learning. But matching net is just one-shot learning. And here we want to see the similarity. So this is our query. We want to see, and these are the images in our support. And we want to know which one has the most similarity. This is like a human child, that we don't learn a deep neural networks. A child, if you just give her just a few, if you just give my niece a few images, she will recognize me and his relatives very easily just by a few examples. So it's a very natural idea, and it's very important, especially nowadays. And so the label for test example can be obtained easily. And this C could be anything. The C between F and G could be anything. So we normalize them, and so you see that it's just a linear combination of your yi's. And this is called attention kernel. And the attention mechanism which fully specifies the classifier. The simplest form that this takes is to use the softmax over the cosine distance. And we have embedding functions f and g. And so the challenge is that it gets embedded independently of other elements in S. So despite the fact that the classification strategy is fully conditioned and the whole support set through P, the embeddings on which we apply the cosine similarity to tend, point, or simply compute the nearest neighbor are myopic in the sense that each element gets embedded by G independently of the other elements. So this is a solution that they propose in that paper. So we say that we propose embedding elements of set through a function which takes input the full set S in addition to xi. So G becomes G of xi and set, and your full set. And G can modify how to embed xi. And the second issue can be fixed with the LSTM with read attention over the whole set S. And so this is the attention LSTM. So the training strategy is very simple. B is the batch. For example, we have a batch and we want to maximize the log probability. And you see that the batch is taken from L, where L itself is sampled, S itself is sampled from L. And so you see that OmniGlot is very easy. We have very high accuracies, and we expect that 20-way accuracy and 5 accuracy to be high on OmniGlot because it's a very easy data set. And so, but ImageNet is easy as well because you know that the matchnext is as big accuracy, is very good accuracy, but sometimes it has low accuracy. Mini ImageNet is more difficult than ImageNet. You see that in ImageNet everything is below 90%, so it's very easy. But Mini ImageNet, you see that it is 46%, 60%. So you know we are in 2023, and still state-of-the-art models are like that. So let's see matching networks. It outperforms Inception. You know, Inception and all of these variants are very important things in computer vision. But MatchNet even outperforms these state-of-the-art models, which is really exciting. And of course, this is an example for language modeling. And you see that, for example, you have a query and you have lots of classes. For example, dollar could be seen in the blank token.